Andrew Huberman, and I'm a professor of neurobiology and ophthalmology at Stanford School of Medicine. Today we are talking about time perception. Our perception of time is perhaps the most important factor in how we gauge our life. And the reason for that is that our perception of time is directly linked to the neurochemical states that control mood, stress, happiness, excitement, and of course, it frames the way in which we evaluate our past. It frames our present, whether or not we think we are on track or off track, and it frames our sense of the future. So let's talk about time perception. And the most fundamental aspect of time perception is something called entrainment. Entrainment is the way in which your internal processes, your biology and your psychology, are linked to some external thing. And the most basic form of entrainment that we are all a slave to all year round for our entire life are so-called circannual rhythms. We have neurons, nerve cells in our eye, in our brain, and in our body that are marking off the passage of time throughout the year. Literally a calendar system in your brain and body. And the way this works is beautifully simple. Light, seen by your eyes, inhibits, meaning it reduces the amount of a hormone released in your brain called melatonin. Melatonin has two major functions. One function is to make you sleepy at night, and the other is to regulate some of the other hormones of the body, in particular testosterone and estrogen. Throughout the year, depending on where you live, day length varies. And as a consequence, the amount of light from the sun that is available to you varies. So when days are long, the amount of melatonin in your brain and body that's released tends to be less. When days are very short, the amount of melatonin that's released and the duration that melatonin exists in your brain and body tends to be much longer. So melatonin correlates with day length. And if we are viewing more light, we have less melatonin. We view less light, we have more melatonin. You see different amounts of light each day, but we have a process in our brain and body that averages the amount of light that you're seeing, both from artificial sources and from sunlight, and measures that off. And it's so exquisitely precise that for a given, say, 8-hour day in the spring, because spring in the northern hemisphere or elsewhere, days are getting longer, that means that the amount of melatonin is getting progressively less and less, and that signal is conveyed to all the systems of your brain and body. And this is why most people, not all, but most people feel like they have more energy in the spring. Conversely, when you have an 8-hour day in the winter, the amount of melatonin that corresponds to that 8-hour day is getting progressively greater and greater. Because why? Days are getting shorter, so melatonin is increasing from day to day to day. Every cell and system of your body pays attention to this, and as a consequence, most people, not all, but most people feel they have a little less or sometimes a lot less energy and a slightly lower mood in the winter months. Now, there are exceptions to this, of course, but the melatonin signal is the way in which your internal state, your mood, your sense of energy, even your appetite is entrained, is matched to some external event. In this case, the event is the rotation of the Earth around the sun. There are other forms of entrainment, meaning the matching of your brain and body to things that are happening in your external environment. Across the calendar year, the amount of testosterone and estrogen that human beings make varies, such that in longer days, they tend to make more testosterone and estrogen than in shorter days. The next level of time, or bin of time, as we say, that we are all entrained or matched to is the so-called circadian time cycle, which is 24-hour rhythm. This is perhaps the most powerful rhythm that we all contain and that none of us can escape from. We all have this circadian clock that resides over the roof of our mouth. The cells in that circadian clock fire, meaning they release chemicals into our brain and body on a very regular rhythm. Not surprisingly, there are periods of every 24-hour cycle when we are very active and we tend to be alert, and others when we are asleep. We have this circadian clock. It oscillates. It goes up and down once every 24 hours and then repeats. Every cell of our body has a 24-hour oscillation in the expression of various genes. They are entrained, as we say, to the outside light-dark cycle because morning sunlight, evening sunlight, and the lack of light in the middle of the night make sure that the changes, these oscillations that are occurring within the cells of our brain and body are matched to the outside light-dark cycle. And I cannot emphasize enough how important it is that your circadian entrainment be precise. Why? Because disruptions in circadian entrainment cause huge health problems. They increase cancer risk. They increase obesity. They increase mental health issues. They decrease wound healing. They decrease physical and mental performance. They disrupt hormones. You want your cells to be linked to the circadian cycle that's outside you. And the circadian cycle outside you mainly consists of when there's sunlight and when there is not. And that's why the simple protocols to fall out of this whole discussion about circadian entrainment are the following. View 10 to 30 minutes of bright light, ideally sunlight, within an hour of waking. Assuming that you're waking early in the day, especially you wake up early in the day, get outside, see sunlight. Do that again in the afternoon or around evening, 10 to 30 minutes, depending on how bright it is outside. Basically, you want as much bright light, ideally from sunlight, coming in through your eyes throughout the day. And then in the evening, you want as little bright light coming in through your eyes. There are other ways to so-called entrain your circadian clock. One of the best ways to do that is to engage in physical activity at fairly regular times of day. You don't have to do it every day, but if you're going to exercise, try and exercise at a fairly consistent time of day. What happens when this circadian clock starts getting disrupted? I mean, this is, after all, an episode about time perception. It's not an episode about circadian rhythms and entrainment. Well, there's a classic study by Ashoff done in 1985 that's now been repeated many times, where they had people go into environments where they didn't have clocks and they didn't have windows and they didn't have watches, and they were sometimes even in constant dark or constant light. And they evaluated how well people perceive the passage of time on shorter time scales. And what they found was really interesting. What they found is that people underestimate how long they were in these isolated environments. So after 42 days or so, they'd ask people, how long do you think you've been in here? And people would say 28 days or 36 days. They generally underestimated how long they had been in this very odd environment with no clocks or watches or exposure to sunlight or regular rhythms of artificial light. In addition, they found that their perception of shorter time intervals was also really disrupted. So if they asked them to measure off 2 minutes, normally people are pretty good at measuring off 2 minutes. People come within, 5 to 15 seconds at most. Well, when people's circadian clocks or circadian entrainment, I should say, was disrupted, their perception of time measurement on shorter time scales of minutes or even seconds was greatly disrupted. And as we'll see in a couple of minutes, that actually causes great problems for how you contend with work, how you contend with challenges of different kinds. You want your circadian entrainment to be pretty locked in or pretty entrained to the outside light-dark cycle so that your perception of time on shorter time intervals can be precise, because the ability to perceive time accurately for the given task or given thing that you're involved in turns out to be one of the most fundamental ways that predicts how well or poorly you perform that thing or task. Next, I'd like to talk about so-called ultradian entrainment. Ultradian rhythms are rhythms of about 90 minutes or so, and all of our existence is broken up into these 90-minute ultradian cycles. When you go to sleep at night, whether or not you sleep 6 hours or 4 hours or 8 hours or 10 hours, that entire period of sleep is broken up into these 90-minute ultradian cycles. However, when you wake up in the morning, many of the things that you do are governed by these ultradian rhythms. For instance, the 90-minute time block seems to be the one in which the brain can enter a state of focus and alertness and do hard work and focus. And then at about 90 minutes, there's a significant drop in your ability to engage in this mental or physical work. Now, everybody from, the self-help literature to the business literature to the pop psychology literature, has tried to leverage these ultradian cycles by saying, if you're going to do something hard and you want to focus on it, limit it to 90 minutes or less. And I am one of those people who's also joined that conversation. And indeed, I use 90-minute work cycles, and I think they are extremely powerful. While this isn't time perception per se, it is, again, an example of entrainment. What are we entraining to? Well, what you're entraining to is the release of particular neurochemicals, in this case, acetylcholine and dopamine, that allow your brain to focus for particular periods of time, 90 minutes or so. And after about 90 minutes or so, the amount of those chemicals that can be released tends to drop very low, which is why your ability to focus becomes diminished. I always get the question, how do you know when the 90-minute cycle begins? In other words, let's say you wake up at 8 a.m., and you just finished a 90-minute sleep cycle. Does that mean that your next 90-minute cycle where you could do work begins right at 8:01? No. The interesting thing about these basic rest activity cycles, these ultradian rhythms, is that you can initiate them whenever you want. You can set a clock and decide, okay, now the focus begins. Now the work begins. And this 90-minute cycle is the period in which I'm going to do work. What you can't negotiate, however, is that at about 100 minutes or 120 minutes, no matter who you are going to see a diminishment in performance. You're not going to focus as well. And that's, again, because of the way that these 90-minute cycles are linked to the ability of the neurons that release acetylcholine and dopamine, and to some extent norepinephrine, the things that give us narrow focus, motivation, and drive. The way that these 90-minute cycles are involved in those circuits. After about 90 minutes, those circuits are far less willing to engage, and therefore it's much harder to continue to focus to a high degree. Some people like to do multiple 90-minute cycles per day of focus. In that case, you need to separate them out. You can't do one 90-minute cycle, then go right into another 90-minute cycle, then another 90-minute cycle. You can't cheat these circuits related to acetylcholine and dopamine and norepinephrine, unfortunately. For me, I can do one mid-morning. I can probably do another one in the afternoon. This is not the kind of work that's like checking email or text messaging or social media. This is very focused, hard work. It's working on hard problems of various kinds. And this will differ for everybody. So I recommend that they be spaced by at least 2 to 4 hours. And most people probably won't be able to handle more than 2 per day. There are probably some mutants out there that could do 3 or 4, but that's exceedingly rare. I think even 1 a day is going to feel like a significant mental investment. And afterwards, you're going to feel pretty taxed. So now we've talked about circadian, and ultradian rhythms. But we haven't really talked about time perception per se. We've mainly talked about the subconscious, slow, oscillatory ways in which we are entrained or matched to the year or to the day, and these ultradian cycles that we can impose on our work and that we can leverage toward more focus if we like. But what about the actual perception of time? What actually controls how fast or how slowly we perceive time going by? There are basically 3 forms of time perception that we should all be aware of. One is our perception of the passage of time in the present, how quickly or slowly things seem to be happening for us. This is kind of like an interval timer, ticking off time. Tick, 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 tick. It's either fine slicing like that or tick, tick, tick. We have interval timers. I'll discuss the basis of those interval timers. We also engage in what's called prospective timing, which is like a stopwatch, measuring off things as they go forward. That might sound a little bit like what I just described, but it's actually a little bit different. For instance, if I told you to start measuring off a 2-minute time interval into the future, you could do that pretty well. But if I told you you had to measure a 5-minute time interval into the future and you couldn't use any clocks or watches or your phone or anything like that, you would have to set the tick marks. You would have to decide how many times you were going to count off during that 5-minute time block. There's also retrospective time, which is how you measure off time in the past. So if I say, last week, I know you went to the park, you did some things with friends, you went out in the evening. How long was it between lunch and when you went to dinner with friends? You probably think, okay, well, I remember I went to dinner at 7 and we had lunch right around 2. You're using memory to reconstruct certain sets of events in the past and get a sense of their relative positioning within time. Okay? So we have retrospective, current time interval measurements, and then prospective time measurement into the future. The beauty of time perception in the human nervous system is that it boils down to a couple of simple molecules that govern whether or not we are fine slicing time or whether or not we are batching time in larger bins. Those molecules go by names that maybe you've heard, things like dopamine and norepinephrine, neuromodulators, called neuromodulators because they change the way that other neural circuits work. Also things like serotonin. Serotonin is released from a different site in the brain than dopamine and norepinephrine is, and has a different effect on time perception. So just to give you an example of how things like dopamine and serotonin can modulate our perception of time, I want to focus on a little bit of literature that now has been done, fortunately, in animals and humans, and which essentially shows that the more dopamine that's released into our brain, the more we tend to overestimate the amount of time that is just passed. Let me repeat that. The more dopamine that is released into our brain, the more we tend to overestimate how much time has passed. These experiments are very straightforward, and they're very objective, which is really nice, which is you can give people or an animal a drug that increases the amount of dopamine, and then ask them to measure off without any measurement device like a watch or a clock when 1 minute has passed. As dopamine levels rise in the brain, people tend to think that the minute is up before a minute. So at the 38-second mark, they'll say, okay, I think a minute is up. So they've overestimated how much time has passed. Okay. The higher the level of dopamine, the more people tend to overestimate. Now, it's also true that norepinephrine, also called noradrenaline, plays a role, and its role is very similar to that of dopamine. Conversely, the neuromodulator serotonin causes people to underestimate the amount of time that's passed. So this is very interesting. It's interesting in terms of how pharmacology can be used to adjust time perception, but it's also interesting in the context of that circadian rhythm. There's some emerging evidence that throughout the 24-hour cycle, there are robust changes in the amount of dopamine, norepinephrine, and serotonin that are present in the brain and bloodstream and body, depending on time of day within the circadian cycle. So much of the evidence points to the fact that in the first half of the day, approximate first half of the day, dopamine and norepinephrine are elevated in the brain, body, and bloodstream much more than is serotonin. And that in the second half of the day, and in particular towards evening and nighttime, serotonin levels are going up. What that means is that our perception of the passage of time will be very different in the early part of the day and in the latter half of the day. Now, this is important in terms of how one thinks about structuring their day, because I know many people are thinking about the various tasks that they need to do throughout their day. Many, or I should say all of the literature, at least that I can find, on productivity and things of that sort point to the idea that we should be doing the hardest task, the thing that we want to do the least or the most important task early in the day as a kind of a psychological tool for getting it done and feeling as if we accomplished something. And I think that's an excellent protocol, frankly. And as an aside, to support what I said, but also to take us back to this critical role of the circadian rhythm, there is a lot of evidence that when one's sleep is disrupted, when sleep is either too short or is fragmented or is not of high enough quality for enough days, one of the first things to happen is that there is a dysregulation of these dopaminergic, noradrenergic, and serotonergic states throughout the day. Now, there is a version of how dopamine and norepinephrine can impact our perception of the passage of time in ways that can be very disruptive or even maladaptive. And the best example that I'm aware of is trauma. Many people who have been in car accidents or who have experienced some other form of major trauma do what's called overclocking. Overclocking is when levels of dopamine and norepinephrine increase so much during a particular event that we fine slice, in other words, the frame rate is increased so much so that we perceive things as happening in ultra slow motion. Now, that might not seem like a bad thing overall, but the problem with overclocking is the way in which that information gets stamped down into the memory system. So the memory system, which involves areas of the brain like the hippocampus, but also the neocortex, is basically a space-time recorder. What do I mean by space-time recorder? Well, your nervous system, of course, is housed in the darkness of your skull. It doesn't have a whole lot of information about the outside world except light coming in through the eyes and whatever happens to hit our ears and in terms of sound waves and skin and so forth. So it has to take all those neural signals and it has to create a record of what happened. Now, it doesn't create a record of everything that happened, but car accidents and trauma and things of that sort oftentimes are stamped down into our record of what happened. And what gets stamped down, what we actually mean by the phrase stamped down, is that the precise firing of the sequence of neurons that reflected some event. So let's say I'm in a car accident, certain neurons are firing because of the flipping of the car, or there's screams, or there's blood, or things of that sort. All of that neural activity gets repeated in the hippocampus, and then the sequence of the firing of those neurons is also remembered. So it's not just that neuron 1, 2, 3, 4 fired in that sequence. It's also that neuron 1, 2, 3, 4 fired at a particular rate. So it would be 1, 2, 3, 4 during the actual event, and then the memory is stored as firing of those neurons as 1, 2, 3, 4, right? If during the event it was 1, 2, 3, 4 at that rate, the storage of the memory is not going to be 1, 2, 3, 4. Okay? In other words, there's both a space code, as we say, meaning the particular neurons that fire is important, and there's a rate code, how quickly those neurons fire, or the relative firing, the timing of the firing of those neurons is also part of the memory. This affords our memory system tremendous flexibility. What it means is that you can take the same set of neurons in the hippocampus and stamp down many, many more memories, because all you have to do is use a match of the different rates of the different neurons that were firing in order to set that code, right? Otherwise, if you needed a different set of neurons for every memory, you need an enormous hippocampus, you need an enormous head. So I think you get the basic idea. Overclocking is a case in which the frame rate is so high that a memory gets stamped down and people have a very hard time shaking that memory and the emotions associated with that memory. In fact, one of the first things that trauma victims learn is that they aren't going to forget what happened. What's eventually going to happen, ideally with good treatment, is that the emotional weight of the experience will eventually be divorced from the memory of the experience. Some of you are probably saying, why dopamine during trauma? I thought dopamine was the feel-good molecule. Well, in reality, dopamine is not necessarily a molecule of reward. It's a molecule of motivation, pursuit, and drive. And because of the close relationship between dopamine and norepinephrine, oftentimes they are co-released. So whether or not dopamine is released during car crashes or other forms of trauma, we don't know. But what we do know is that both the dopamine system and the noradrenergic system, when we say noradrenergic, we mean norepinephrine, those systems are greatly increased anytime there's a heightened state of arousal. And arousal can have negative valence, meaning associated with an event that we really hate, that we would prefer not to be involved in, or it can have positive valence. But dopamine and norepinephrine are kind of the common hallmark of all things of elevated arousal. And so that's why we see evidence for dopamine being associated with these changes in time perception, both for positive events and for negative events. Now, up until now, I've been talking about how dopamine and to some extent serotonin can differentially impact your perception of how fast or how slowly things are happening in the moment. But remember, we have prospective time, we have our experience of time in the moment, and we have retrospective time. And there are beautiful studies that have showed that the dopaminergic state changes the way, not just that we experience things now, but that it changes the way in which we remember things in the past and the rate at which those things occurred. And those are in opposite direction. So to make this very simple, if something that you experience is fun or varied, meaning it has a lot of different components in it, and is, in other words, is associated with an increase in dopamine in your brain, you will experience that as going by very fast. Imagine an amazing day for a kid at an amusement park. They can do a ton of things. It's all new. They're very excited, and they'll feel like it goes by very fast. But later, they will remember that experience as being very long, that it was a long day full of many, many events. And so there's this paradoxical relationship between how we perceive fun, exciting, varied events in the present and how we remember them in the past. For those of you who have gone on vacation, if you've had an amazing day on vacation, it'll seem like, or an amazing vacation overall, it will seem like it goes by very fast. The last day of vacation, you sort of go, whoa, it went by so fast because there's so much happening. But in memory, 6 to 8 months later, you remember, wow, that just went, that was a long, long thing. We had this, then we had that, then we did this, then we had that. It tends to spool out in a longer memory than the actual experience. Conversely, if you're bored with something, or it's something you really don't like, it's going to seem like it takes a long time to go through that experience in the moment. But retroactively looking back, it will seem like that moment was very short. And so the reason I bring this up is we aren't just driven by these circadian clocks and these circannual clocks and these ultradian clocks. We are driven by these timers that vary depending on our level of excitement. And they vary depending on our level of excitement because of these neuromodulators, dopamine and serotonin. So the way I like to think about it is that you have two clocks, two stopwatches. One is a dopaminergic stopwatch that fine slices really closely. It's like counts off milliseconds, and it's grabbing a movie of your experience at very high resolution. And on the other hand, you have a stopwatch that's gathering big time bins, big ticks along the hand is moving at bigger intervals, marking off time. And depending on whether or not you're excited or whether or not you're bored, you're using different stopwatches on time, and therefore you're perceiving your experience differently. One very interesting aspect to the way that neuromodulators like dopamine and novelty interact with time perception and memory is how we perceive our relationship to places and people. So really interesting literature showing that the more novel experiences we have in a place, the more we feel we know that place, obviously, but the longer we feel we've been there. So here's the kind of Gedanken or thought experiment that illustrates what's in the literature. Let's say I were to move to New York City. I happen to really like New York City. I've never lived there, but let's say I lived there. I lived in a given apartment for a year, and I would have a number of different experiences. In this mental experiment, let's say I had 100 different exciting and new experiences. I would, at the end of that year, feel as if I lived there a certain period of time, 1 year. I would actually know I lived there 1 year. If, however, I lived in 3 different places in New York City and I met 3 times as many people and I had 3 times as many novel experiences, I would actually feel as if I had been there much longer than had I only lived in one location. This is also true for social interactions. When we move to multiple or several novel environments with somebody else, we tend to feel as if we know that person much better and that they know us much better. Now, that's all very interesting and speaks to the fact that dopamine is a kind of flexible currency in the brain. It's doled out, if you will, or released when something that one hopes will happen happens, and it's released when there's a surprise, even if it's a kind of a negative surprise. It's not something that the subject wanted to happen. But the more interesting thing is how that relates to time perception. What I mean is how often and when you release dopamine is actually setting the frame rate on the entire perception of everything, not just for positive events or negative events. This governance over our perception of time that dopamine has points to a very clear, very actionable, and very powerful tool. And that is a tool that many people have talked about before, which are habits. People have discussed habits in a variety of contexts, but in the context of dopamine reward and time perception, what this means is that placing specific habitual routines at particular intervals throughout your day is a very, not just convenient, but a very good way to incorporate the dopamine system so that you divide your day into a series of what I would call functional units. What would this look like? It would mean waking up and having one specific habit that you always engage in that causes a release of dopamine. You could say, well, great, that'll make me feel good. And I would agree, dopamine release generally makes us feel motivated, but it would have an additional effect of marking that time of day as the beginning of a particular time bin. then inserting another habit, perhaps the beginning of, your breakfast or something, but recognizing that that's a habit and being fairly habitual. You don't have to be, obsessively precise about the timing, but that regular sequencing of things is going to lead not just to dopamine release as it relates to reward and motivation and feeling good, but it actually becomes the way in which we carve up our entire experience of our day. Today, we covered a lot about time perception. We certainly didn't cover everything about time perception, but we covered things like entrainment, the role of dopamine, habits, and various routines that can adjust your sense of time for sake of particular goals. If you're interested in learning more about time perception, I'd like to point you to a really excellent book called Your Brain is a Time Machine, The Neuroscience and Physics of Time. The book was written by Professor Dr. Dean Bornomano, who's a professor at UCLA and a world expert in the neuroscience and physics of time. Thank you for your time and attention today. And last but